Welcome to Quad Drone Lab. We're about to tear down the single most important part of your drone, the one thing that truly defines its flight time, its power, and what it's ultimately capable of. Yep, we're talking about the battery.
All right, so here's how we're going to break it down. We've got 5 main sections. We'll start with the absolute basics, the foundational stuff, and then we're going to work our way all the way up to the cutting-edge tech that's completely changing the game.
I know. That sounds like a pretty bold claim, right? But honestly, it's the absolute truth. If you really want to unlock a drone's true potential, we're talking max endurance, insane power, and rock-solid reliability, you have got to master the battery.
Okay, let's dive right in. The very first thing any drone engineer has to grapple with is this fundamental choice between the 2 main battery types. And trust me, it's a constant balancing act, a trade-off between how long you can stay in the air versus how nimble you can be. So, what's it all boiled down to? Well, it's really about power density versus energy density. Think of LiPo batteries as your world-class sprinters. They're built to deliver an incredible, massive burst of current, perfect for those wild, aggressive maneuvers you see in FPV racing. Leon, though, that's your marathon runner. It's all about energy density, cramming as much energy as possible into every single gram. And that's absolutely what you need for those long-haul missions. You know, things like mapping or surveillance. And this table, wow, it just lays it all out so clearly. This is that mission-critical trade-off I was talking about. Look over at the LiPo column. See that discharge rate? It can be 50 C, even higher. That's the punch, the raw power for racing. But then you look at the energy density for Lion. We're talking up to 450 watt-hours per kilogram. That's potentially more than double what a LiPo can offer. And that right there, that's the magic number that gets you those 60-minute-plus flight times that the pros absolutely depend on. Okay, so we've got these 2 types. But how do you actually tell what a battery can really do? You know, how do we cut through all the marketing noise and get to the metrics that actually matter? Well, that brings us to our next section. You've seen it, right? These batteries with massive C ratings plastered all over them, 130 C. But here's the deal, and this quote nails it. For those in the know, C rating has pretty much become a marketing gimmick. The real performance is way, way lower. The one number that actually tells you the truth, that's internal resistance. So, what is internal resistance, or IR? The easiest way to picture it is like electrical friction inside the battery. The more friction you have, the more of your precious energy gets wasted as heat instead of spinning your props. So a lower IR is always better. It means less energy wasted, which directly translates to less voltage sag when you slam the throttle, and just way more consistent power. And this, right here, is why if you're managing any number of batteries, tracking IR is absolutely non-negotiable. Seriously, this table from Group AO is basically your health chart. You see, a brand new cell, it might be down around 1 milliohm, super healthy. If it climbs to, say, 2 or 3 over time, you're still in the green. But the moment you start seeing numbers creeping up towards 8 milliohms or more, that battery is a liability. It's not just about poor performance anymore, it's a major safety risk. You have to retire it immediately. All right, so we've talked about the cell. Now let's zoom out and look at the whole system. Because there's a huge trend happening in the pro drone world right now, and that's the move to high voltage systems. So you might be asking yourself, why? Why is everyone moving away from the 4S and 6S packs we're all used to and jumping to these massive 12S 44.4 volt systems, especially for the big industrial drones? Well, the answer is, it's all about physics. It's about a massive leap in efficiency. And boom, this chart just says it all. Check this out. To get 1,000 watts of power, which is a pretty standard amount, look at what a 4S system has to do. It has to pull a whopping 67.5 amps. Now slide your eyes over to the 12S bar. It's delivering the exact same power, but it's only pulling 22.5 amps. That's 1/3 the current. I mean, that one single fact changes absolutely everything. And that huge drop in current, it has this incredible ripple effect through the entire system. You might remember this from your physics class. Heat loss is equal to current squared times resistance. So when you cut the current by a factor of 3, you're actually slashing the heat generated by a factor of 9. That's a dramatic difference. We're talking cooler motors, cooler ESCs, less stress on everything. You can even use thinner, lighter wires, which saves weight. It all adds up to a drone that's just way more reliable and easier to maintain. Okay, so we've got power and efficiency nailed down. But what good are they if your system isn't reliable? That brings us to the unsung heroes, the systems that support the battery. All right, here's a fun fact that actually surprises a lot of people, even folks who have been building drones for years. You see the battery in your phone or your laptop? It has a smart little computer inside called a battery management system, or BMS. Your high-performance drone battery? It probably doesn't. Yeah, for the most part, they are intentionally dumb packs.
And why would they do that? Well, it's all about saving every last gram of weight and making it super easy to swap packs in the field. But here's the catch. It means all that critical intelligence, the stuff that balances the cells, monitors voltage, and keeps things safe, it all has to live somewhere else. And that somewhere else is the drone's flight controller. So the drone itself is responsible for protecting the battery. And that's why having a solid plan for managing heat isn't just a good idea. It's absolutely 100% critical for safety and for getting the most life out of your packs.
So, what does that look like in the real world? Well, it's a spectrum, as you can see here. For your little FPV drone, simple passive cooling, just air flowing over the battery, is usually fine. Step up to a big agricultural drone spraying crops. Now you're going to need active, forced air cooling. And then you get to the really big stuff like eVTOLs. These things are pulling so much power, you have no choice but to use complex, active liquid cooling systems. The big takeaway is you have to match your cooling solution to the demands of your mission. All right, for our last section, let's look over the horizon. Let's talk about the future. What's coming next? What are the new battery chemistries that are getting ready to completely shatter the performance barriers we have today? Okay, the biggest breakthrough that's happening right now is the shift away from the traditional graphite anode in batteries. The new hotness? Silicon anodes. And companies like Amprius are really leading the way here. The science is amazing. Silicon can hold something like 10 times more lithium ions than graphite. So what does that mean for you? The result is just mind-blowing. For the exact same battery weight, we're talking about the potential to double your flight time. And I want to be clear, this isn't some far-off lab experiment. This stuff is real. Look at this data from Amprius. Their Psycore platform is already hitting 450 watt-hours per kilogram. That's enabling brand new missions for things like high-altitude drones that can stay up for days. And then there's their Cymax platform. It's breaking through the 500 watt per kilogram barrier. That's a level of energy density that was just a dream a few years ago, and it's a total game changer for top-tier aerospace and defense projects. But even with all that, what's the ultimate goal? The real holy grail of battery tech? That would be the all-solid-state battery. The idea here is to get rid of the flammable liquid electrolyte inside current batteries and replace it with a solid material. If we can crack that, it could basically make thermal runaway and battery fires a thing of the past. We're talking about a whole new level of safety and performance. So when you step back and look at the whole picture, the progression is just incredible. From the super short flights of the early LiPo days to the long endurance missions we can do now with Lion. And looking forward to the revolutionary potential of solid state, it's crystal clear that battery tech is the engine driving drone capabilities forward. And look, for any serious engineer, for any researcher in this space, keeping up with this stuff isn't optional anymore. It's absolutely essential if you want to stay competitive. So if this deep dive got you excited and you're thinking, I need to know more, then we've got the perfect next step for you. We'd love for you to join us over at the Quad Drone Lab membership here on YouTube. When you join, you get access to everything. Our full in-depth video labs where we test this stuff, complete breakdowns of the latest research papers, and you even get access to our exclusive data sets in Python code. Honestly, it's the single best way to get the tools and the expert Q&A you need to really lead in this field. Just click that join button below and get your edge.